I think I won't have that many Greek letters. I will have some Greek letters. So if you're a Greek letter person, there will be some. But I've sort of my background is I've done some work in programming language theory, and I've also actually written some code, some open source F# software, and I've been going to a lot of conferences, and one thing I found really interesting is that there's quite a lot of communities that talk about errors in different ways. So this talk is sort of trying to have a more historical and more philosophical take and sort of take a step back and think about errors. So how many people had errors in their code recently? Yeah, it's a stretching exercise after lunch. The fun thing about errors is that if you look at the history, the very early history of computing, then what Charles Babbage said on errors is that if you run trials over 3 or 4 simple cases, and it agrees with the results that you get from the machine, then it's scarcely possible that there can be any error. So Babbage thought when he builds his analytical engine, he'll just run it on 3 simple cases. It works. Fine, we're set. Ship it. Okay, Babbage was a long time ago. This was written in 1837. So maybe we sort of got better at this. But if you look back at the history of modern computing, then the idea in sort of early electronic computers around ENIAC was that the ENIAC woman would simply set up the machine to perform these plans provided by those men programmers. And nobody really expected that this would turn out to be difficult and require radically innovative thinking. And I think this is a fantastic sort of historical point because it also sort of shows you that the women who were programming all those ancient crazy computers had to be super clever. And once men realized that this is actually hard work, they started doing it all themselves. This was the sort of period where all the computing work, all the sort of programming, people or the men doing the work thought this is easy, we can give it to women. And it was actually really hard. So ENIAC is a crazy parallel machine that I think even sort of people these days are actually trying to figure out how the hell did it actually work. So in the early computing times, people still didn't really think that programming was hard. It was just like someone will come up with a sort of vague specification, and then the programmers will do all the work. It sort of took a few more years. So ENIAC was like end of 40s, I think. And by the end of 60s, people actually finally realized that programming is difficult. And many were talking about a programming crisis. And this actually sort of continued over and over the history of computing. So this is a quote from a fantastic book that sort of traces the history of computing or some of the sort of people around computers. This is sort of saying that for the next several decades, managers, academics, and governments would release warning about the desperate state of software industry with ritualistic regularity. So there was a crisis at the end of 60s, there was crisis at the end of 80s, there was crisis with the year 2000. Computing is always in a crisis because its programming is so difficult. This is actually a joke magazine, but it's not too far from reality. In the year 2000, everyone was expecting that basically the whole world will end. How many people still remember this? Yeah, good. Most people do. Because the date issue, so airplanes will fall down from the skies. And there's always some crisis. And one interesting sort of point that Nathan Ensminger makes in that book is that it looks like computing is always in a crisis. We can't write software that works. And still, it's somehow the most successful and profitable industry of all time. So turns out that people somehow probably can manage write software. It doesn't always work, but it sort of mostly works. And I think that's sort of the interesting sort of point here is that we have actually, over the last 50 years, found quite a lot of different ways of thinking about errors and dealing with errors. And so what I want to do in this talk is to go through a couple of different approaches where people have somehow found ways of dealing with errors, and there's quite a lot of different communities that do it in different ways. I'll talk about four main ideas that are sort of jokingly represented here by these four characters. So the first thing is sort of treating errors as part of the programming process. And this goes all the way to the ancient programming language of COBOL. In 60s, COBOL was used. COBOL is actually a fascinating language because if you go to university, nobody will tell you anything about COBOL. They don't even admit it exists. Because COBOL comes from this sort of data processing world, which was in the early history fairly disconnected from the academic world. And in those communities, the basic sort of problem or the basic thinking was that it's really hard to do programming because programmers are such prima donnas and they cost a lot of money and you have to like be nice to them and keep them around. That what we really need is to find sort of managerial approach where you can just hire lots of low-skilled programmers and use them somehow to solve the complicated problems. And if someone leaves, you can just replace them. So a lot of the early thinking here was how can we actually turn programming into software engineering where there's a proper process, and the process originally meant more sort of management process. And the big sort of event that historians often refer to as the NATO Conference on Software Engineering in, I think, 1968, where the goal of the conference is to find a way to sort of replace the black art of programming with a science of software engineering. So programming was perceived as this sort of mysterious skill that you either have or don't have, and it's really hard to find people who have it. And the idea was we need to come up with sort of proper methodology, and that's what ended up being called software engineering. This was very much sort of rooted in that managerial approach. I think that there's sort of interesting history if you go from the 1968 to the current time. Then in the 1968, people were like, software programming isn't a craft or black magic. It's an engineering discipline. There should be order and methods and so on. And if you look at Software Craftsmanship Manifesto, this is emphasizing the skills of the individuals and interactions over processes and tools. So I think there's sort of an interesting historical point where in the end of 60s we were like, well, we have to turn this into we have to focus on the processes and tools, and now that's sort of coming back. That like all of these are really sort of thinking about the errors and eliminating the errors through how humans work as programmers. So should we sort of have a framework for working that's mostly sort of management techniques that will somehow eliminate the errors, or should we sort of give individuals more trust and sort of focus on that side to eliminate errors? One thing I find really interesting is if you sort of think about how test-driven development deals with program errors. So this is just to sort of quote. So in TDD, the idea is that we drive development with automated tests, and you first, well, you only write new code if some test has failed, and then you do some refactoring and eliminate code duplication. But here, the really interesting idea, I think, is that TDD is taking errors as sort of first-class thing in your programming process. So you develop basically by creating errors. You do sort of add a new test that fails, that creates an error, and then you eliminate the error by writing some code and making that code better. So this is an interesting sort of methodological approach that takes the error as a thing that you actually use to drive your development. This way, the error actually sort of becomes a medium for information because tests become a specification of what your application should be doing, and they sometimes become a sort of documentation that documents what actually, how different APIs behave. So if you come to a project that has good tests, you can often sort of look at the tests to see how to use things and so on. So this is really sort of taking errors and making them a part of the development process as something that's very close to the human. Now, you don't really expect that the errors will happen when you deploy the application. You just use them in the development process, but they're part of the process in a way. Now, so that was sort of approach that appeared in the data processing industry in the 60s, and I think you can trace it to modern sort of software engineering, software development approaches like Agile. In a parallel universe over in the universities, errors were treated in a very different way. So this is a quote from an early article in ACM, which is the sort of academic journal, and it says, well, we ACM people have read some articles written by the data processing COBOL people and found them lacking. They suffer from one basic fault. They fail to report fundamental research in the data processing field. So people in the universities felt that this is just not sort of solid research enough. Like there's no fundamental results. And what were the universities doing instead? Well, the one sort of remarkable thing that happened around that time was the ALGOL programming language. People in the academic world sometimes treat it as remarkable computer science achievement. They say it's an object of beauty, but it was never really widely adopted. How many people have written some code in ALGOL? Yes, nobody. It's also pretty old, but the sort of interesting thing about ALGOL for the academic world is that it had this like very formal mathematical description. So the whole idea of describing a grammar of a language is something that first happened in ALGOL. The whole idea of describing formal semantics of a language, what does it actually mean? That's something that comes from ALGOL. And even though nobody really sort of, well, few people used it, it took surprisingly long time to write a compiler for it because it was so difficult. But the really sort of achievement here is that it defines an academic programming agenda. So ALGOL defines something that people later call the ALGOL research program. And that's the idea that you can utilize the resources of logic to increase the confidence in the correctness of program. And instead of debugging a program, you should prove that it meets the specification. So this is the approach to errors that sort of lived in the academic world, where people thought all this like fiddly stuff with running programs and having managers to control errors, that's just like because they can't do it properly, right? We should prove that your program is correct using mathematics, and then it will be correct. And this idea is something that you can sort of trace through the modern sort of academic approach to programming. So if you want Greek letters, lots of the TAUs with type systems, that's about ensuring or proving sort of formally that some of the errors in programs cannot happen. And today there's sort of even more extreme idea with dependent types, languages like Idris or Agda, where people really want to ensure that the type of a program checks even more than just like this returns a number. They want to give you this returns a valid date in this range, for example, and so on. So there's a recent book which says, today most people who write software assume that the cost of formal verification, basically proving your program's correct, is still too high. And this book is trying to convince you that finally we have sort of enough good enough formal tools that you can write formally verified programs. And I think this is sort of fascinating history, because if you go from Algol to modern sort of work on fancy types, people were telling you for the last 50 years that now we are almost there and we almost have it, and now you can finally give it like 2 more years and we will prove that your program will be correct. But I think it's also sort of very interesting as like you can see why this resonates well with academic circles, because you're using mathematics, which is a sort of foundational tool in sciences, to talk about computers as well. So it is a logical approach, and sometimes it's useful, sometimes not so much, I would argue. But it's sort of an approach to errors that has been existing pretty much in parallel with many others over the last 50 years. And we always just say, give it 2 more years and then we'll have it working perfectly. So one of the people who really sort of work in this area is Tony Hoare, who at some point, I think this is sort of 90s or so, wrote a paper, How Did Software Get So Reliable Without Proof? So, and in the paper, he looks at the cases where humans were killed by, or he tries to count the number of cases where computers killed some humans, and he finds surprisingly small number of those. So how is it that computers haven't yet destroyed the humanity, even though we can't prove that they're correct? And I think his sort of answer, so I find this really interesting because it's sort of honestly admitting that even though people aren't proving things, they're actually writing code that somehow mostly works. I think his answer to the question is sort of, well, people probably just use sort of reasonable engineering methods, and I don't think the answer is all that interesting, but I like the fact that he wrote this paper. So that's some of the approaches. There was the sort of data processing and managerial. There's the formal academic and proving things. And I have 2 more. So this one is, and I think that the context where it appears is very much telling. So this idea is that errors are unavoidable even during the runtime. And it's something that appeared in the telecommunications industry, where you have large networks, lots of small devices, that lightning can hit them, they will break. And that's, of course, what Erlang is doing. In Erlang, you have a context where parts of your system will inevitably die or break. And errors will just happen because of the scale. So that context, I think, gives people who designed the language sort of very different way of thinking about errors. And This is from Joe Armstrong's PhD thesis. Is Joe around here? No? Well, you can get his PhD thesis and read everything about Erlang's approach to errors. And what he's saying here is that he's sort of differentiating between two things. Exceptions occur when the runtime doesn't know what to do, and errors occur when the programmer doesn't know what to do. And the errors are expected because specification will never cover all the cases. Like if you have a sort of telecommunication system that spans the whole globe, even a cosmic ray can flip a bit somewhere, and your specification isn't going to say what to do in that case. So the Erlang approach is this "let it crash" slogan. So to quote Joe, he says, "What kind of code must programmer write when they find an error? Well, let some other process fix the error. But what does this mean for the code you're writing, where you actually get the error? The answer is let it crash." And here the idea is that you will write code, and when you don't know what to do, you'll just kill the process. And Erlang handles this. Erlang handles this through the sort of supervision system, where you will have some other process that will monitor all the little processes, and if they crash once, restart them. If they crash 10 times, maybe try to some other way of doing what it wants to do. So you just say, errors will happen at runtime, and I just have to have some recovery mechanism for handling that. I think there's a sort of interesting link with the errors in the TDD world, because in TDD, what I was saying is that the errors are sort of specification. They're telling you what to do, and you remove them later on. In Erlang, they're the lack of specification, because they're saying, if I don't know what to do, I'll just have an error. The funny thing here is that you really expect that the errors will happen. So are they still errors? Well, Erlang people talk about them like errors, so they probably are errors. But if you show this to a formalist from the academic world, they will say, well, no, this is not an error if you're expecting that it will happen. And you should write more complicated proofs about your Erlang programs. But I think they really are sort of the same kind of error. So that's third approach coming from the telecommunications world. And I have one more, and you'll see this one in action tonight if you stay for Sam Aaron's performance later on. This one, so in the very early history, I think this is just more of a curious remark than really the origin of the idea. But a curious remark was that when people thought that programming was black art, people did some research on trying to figure out what other sort of skills correlate with good programming skills. And all this research was pretty bad. They sort of had small samples. The famous sort of 10x developer, I think that was done on sample of like 15 people or 10 people. So it really has like no statistical significance whatsoever. But it became a meme in the community, and that's why it people keep saying those things. And one of those memes was that the sort of personality profiles that suggested that programmers where good programmers had uniquely creative ability like chess or music. I think that, so this bit of the talk is really focusing on the music side eventually. But when something of this, when sort of this approach to error first appeared was in 1970s with Smalltalk, and this is from another fantastic book about history of programming written by Mark Priestley, who says that the Smalltalk approach to design of a language was really very, very different from what the Algol people were advocating. So in Algol, you have this approach that you will sort of define a formal grammar using mathematics and logic. And in Smalltalk, they just went about it in a completely different way. And the idea was that programming wasn't thought as the task of creating a linguistic formal entity, but rather as a process of working interactively with some representation of the program. One thing that I find sort of extremely, extremely sad is that if you go to Wikipedia and search for Smalltalk, and you read the Wikipedia page of about Smalltalk, it sort of says, here's the grammar of the Smalltalk language, and here's the Smalltalk syntax. And that's exactly not the kind of thing that Smalltalk was about, because Smalltalk was more about interactions with the system. So if somebody is a Smalltalk fan, please go and fix Wikipedia. Really, it was more about the interactions, and I think that's sort of how I want to get back to the music part, because if you go see Sam's performance tonight, what he's doing is this sort of live coding where you write code and it plays music, the live coding approach to errors is very different, because if you're and people have sort of linked it to musical genres like jazz, where in musical genres that are not so closely annotated, there are no wrong notes. There are only notes that are more or less appropriate for the performance. And in live coding, it's very similar, because there are no sort of obviously wrong things. They're just things that work better and work less well. So what does a live coder or person writing sort of code to run music do when there's error? Well, they may prefer to accept the results of imperfect execution, and maybe they could sort of compensate for an unexpected result by some manual intervention, or maybe even accept the result as an alternative and develop it further. So in sort of live coding, when you're writing code, it's really more about the interaction, because you type something, you hear how it sounds. If it sounds good, then it's not an error. If it sounds strange, then you have to somehow compensate for it. But maybe that actually will develop into something even better than what you were planning. So it's not necessarily an error in the sort of strict sense. I sort of talked about this in the context of music and live-coded music, and you'll see that in action tonight. But it really is more sort of general approach, I think, because you can really sort of focus on the human interaction. And the thing that these systems let you do is to quickly intervene. So they make the errors sort of more obvious. In live-coded music, you will just hear that something is not right. If you have some monitoring system or a Smalltalk system, you will sort of have some window that shows you the status, and you'll see that something is not right. And you have to be able to quickly fix it. If you're doing something like data science, in data science, a lot of work is more interactive, sort of fiddling with some data in a REPL. And I think that's really sort of treating errors in a similar way, because you run some analysis, you see some results. Do you immediately know whether there's an error or not? Well, sometimes not really. Like you might have a bug in your algorithm, and it would still give you results that are sort of vaguely right. So it's more about the sort of interaction and fixing the error on the fly interactively. So let's sort of look at a couple of famous errors from the recent history. So this is a great error where Google Translate at one point, I think if you were translating from Russian to Ukrainian, it would translate Sergei Lavrov as said little horse and Russia as Mordor. Is that an error? Who thinks it's an error? Okay, well, who thinks this is correct? Yeah, so this is a hard case, right? Because the way the reason why this happened is that Google Translate is learning from sort of what people write on the internet, and I think they're sort of searching for words appearing in a certain context. And Ukrainians, after the invasion, started really sort of writing consistently, referring to Russia as Mordor and referring to Lavrov as sad little horse. So the one interesting or important learning lesson from this is I think that really you have to think of errors as socio-technological entities. They're not just, there's no sort of objectiveness to what is an error. It always depends on the social context. And that previous case is one example of that. There's even sort of more worrying examples from the recent history. But we have to sort of think of errors in a more broader context. So formally, that Google Translate code was right, but it could cause a war. So that's maybe an error. This is another great case. So this is a trading firm that, what's the number? Lost 400 million because they had a software bug. What happened is that they had sort of some system, and at some place in the system there was like a flag that was no longer used. So they rewrote the code so that when this flag is on, it does something new, something clever, and deployed a new version, turned on the flag. But it turned out that on one of those systems they deployed, they still had run, the old version was still running there. And so when they turned on the flag, it turned on some piece of code that wasn't supposed to be used anymore, and it started selling things at the wrong price, which cost them this amount of millions. Now, I think this is really interesting because it sort of lets you see how the different people would react. So if you talk to someone who does live coding, they will say, well, this is ridiculous because it took them 45 minutes to shut down the system, which it really did. Like, they didn't know what's happening, and they didn't know how to react. So if you had a live coding system where you see that something is wrong, you should be able to quickly intervene and fix the error live. And maybe it would cost them $1 million, which is fine for them. They were a rich hedge fund, but they would sort of fix the problem in production quickly. In Erlang, you would say, well, this like business with flags, that's all messy. They should just introduce a new kind of message, and then the old server would crash and don't do anything. The live coders have one solution to the problem. The Erlangers have one solution to the problems. The formalists will say you should just prove that your system is correct. You might sort of object that actually this is really hard here because the problem was in the sort of two different versions. So they'll say, well, you should prove that your deployment script is also correct and that all possible combinations of versions are correct. It gets pretty tricky, but there are definitely sort of approaches that follow the formal method as well. And then the craftsman or the sort of software engineer might say, well, they should have had some decent tests. The sort of interesting question here is what tests would they actually have? Like, this is a case where we're you would have tests for the current version, but the case with sort of multiple versions competing, that's quite tricky. You might have some test that says, well, sort of for all other inputs, it doesn't do anything bad, but it's a tricky case. But the main point here is that sort of each of these different communities thinks about errors in a different way, and I think this case with the financial loss is really good one where you can see that there's multiple ways of answering those questions, and none of these is quite perfect. One is sort of you still lose some money. The other that one would probably work pretty well here. This one is expensive. Here we don't really quite know how to do it. So I think which approach you choose is very sort of context specific. Another error, so this is the famous Y2K problem. I think this one, so here, there's sort of what people tried to do before the year 2000 was that sort of many people tried to fix all the old systems and tried to sort of write tests, fix the bugs. And this is more sort of software engineering or proving. It hasn't been done upfront. It sort of came later. But the problem was like, what's the actual sort of formal property here? Because in formal land, we will always have some abstractions. So date would probably, you would just say, well, date is just a mathematical entity that is ordered. And then you're just ignoring the actual physical representation. What people did as well was that around the sort of midnight before the year 2000, there was like lots of people just actually sitting in all the computer rooms, sort of ready to make the manual intervention if the system behaves badly. So this is sort of mix of engineering and live coding, where people were actually sitting there ready to do live coding, except that the systems that they were trying to fix live didn't have any good live coding interface. If sort of all of these systems were written in something like Smalltalk, then you could actually inspect the values and do the fixes live, which of course sort of no other systems really let you do, because you can't easily inspect and modify the system while it's running. I think the case here with Y2K is sort of interesting, because in a way, if you're on call and something starts going wrong in your system in production, what you really need is to be able to sort of see where the errors are, have a good way of finding them, and have a good way of fixing them as quickly as possible by manual interventions. But because none of those systems are actually sort of built in that paradigm with the live coding in mind, you just have really crappy tools for doing those fixes. So to wrap up and to leave some time for questions, I talked about 4 different approaches to handling errors. One is the sort of software engineering, have the right process for doing things and avoiding errors, but acknowledging that they might be part of the development process. The other is the academic. We prove that programs are correct. The third one is the Erlang-inspired. Errors will happen. We have to react and somehow sort of write system that recovers itself. And the fourth is the live coding approach, where you say, well, errors will happen, and we have to have humans to intervene and fix them. So that one might be able to help you with Russia and Mordor. And errors are such a sort of important theme that it's really curious that it keeps repeating itself sort of in this crisis narrative about computing. So I mentioned this before, but this is just a sort of super exciting point that we've been talking about errors for 4 decades, and we've been worried about them, and somehow we still manage. And I think the summary is that you just have to mix all those different approaches, and sometimes it's easier to write the formal specification, sometimes it's just easier to write the code, and having sort of live coding environments where you can intervene and fix the errors is another really important component. Thank you. And I'll answer some questions and leave a slide with these 2 books, which are great. You should read them.
Thank you so much, Thomas. So there are no questions coming in the app at the moment. So are there any questions in the audience at the moment?
Even complaints, I think. There's a
We've got ratings coming in. It's looking pretty good.
Wow.
Yeah.
I try to upset everyone equally.
Don't be shy. Don't be shy. Okay, well then.
We can ask people what they think is the right approach. Who thinks software engineering is the right approach? Who thinks we should prove everything correct? Come on, at least some logicians. Yay. Who thinks we should let software crash and recover? Yeah. And who thinks we should just fix things like life? Yeah. Well, I think this was a well-balanced audience then. So I hope I upset everyone. Question? Yeah, perfect. We've got one question here. Do you want to? Should we get him the mic? All right, I'll repeat it. Mm-hmm. Yeah, so the question is about the sort of proving things, and I mentioned there's more work on this recently. So I know there's like the one branch that I was referring there is sort of called dependently typed programming, which is the idea that you will put more information in the type about what your program is supposed to be doing. And the languages to look for is Idris, so it's IDRIS, and another one that's in this area is F***. And like some of the work they've done is really interesting, where like you can formally specify properties of cryptographic protocols, and then you have sort of proof that your implementation of that is correct. And I think that's really sort of a really interesting approach for things that are very like low level or very sort of everything depends on them. Like everything depends on your cryptography being right. Like if you have a tiny error, you can't live code your way out of it. So that's one thing. There's also work on sort of formal verification, which I'm not that familiar with, but I guess if you search for formal verification, then you'll just find a good description of the current tools in that space. Thanks.
Any other questions?
Well, if there are no questions, then you can find me and chat with me later as well. Thanks for coming.
And perhaps redundantly, don't forget to rate the talk